This is Mrs. Palmer-Quay with the second video for Module 13. In this video, I'm going to continue our discussion of enthalpy with a short talk about the enthalpy of formation and also a little bit about Hess's law. Just to remind ourselves, enthalpy is the measure of the internal energy of a substance, but we can only measure it when a change happens, and we call that delta H. Energy must be absorbed to break the bonds in a chemical reactions and then is released when bonds form because two elements will combine to make a molecule when the bond is a lower energy state than the elements are naturally. The net change then determines if the reaction is an exothermic reaction, which would be a negative delta H, or an endothermic reaction, a positive delta H. Delta H is typically measured as the heat released, expressed in the units of kilojoules per mole, and usually this is done with a calorimeter, which we did way back at the beginning of the school year. So you were introduced to the calorimeter well in advance to this module on thermodynamics. In the previous video, I talked about how we could determine the enthalpy of a substance by looking at bond energies and by adding together all of the energy that would be needed to break the bonds of the reactants in a particular reaction and how much energy would be needed to remake the bonds on the product side of that reaction, and so you can then get a value for the enthalpy of a reaction. There's another way also to get a prediction of the enthalpy of a reaction, and that's by using information from the formation of the various components of that reaction. A formation reaction is a fairly straightforward reaction, as you may remember, where you are combining two things together to make something new. In this case, we're talking about combining element A with element B, and we'll make compound AB. If this reaction is done under standard conditions, and standard conditions are considered 25 degrees Celsius and 1 atmosphere, so basically room temperature in your chemistry laboratory, if you do this reaction under standard conditions, then the change in enthalpy that can be measured if you make 1 mole of the substance becomes known as the standard enthalpy of formation. It's also sometimes called the heat of formation. Then this value can be used to calculate the change in enthalpy in a particular reaction. And this becomes a little bit easier, a lot less math, than if you are calculating bond energies. In the enthalpy of formation reactions, the elements are assumed to have an enthalpy of formation of 0 in their standard state. So because they just naturally would be falling into that standard state, they don't have any enthalpy of formation. Those would be the standard, just the elements alone, but for your elements that are in a homonuclear diatomic, then those would be considered the standard state. So oxygen is as an O2 molecule is its standard state, not just one oxygen by itself. So the standard enthalpy of formation, which is abbreviated delta H subscript F, gives you for any substance that has been formed from its elements, and it can be negative or positive depending upon what the substance is, because even making any compound can be an exothermic or endothermic reaction. It also varies with the phase of the compound. So I have two examples here, water vapor, water in the gaseous state compared to water in the liquid state. You can see that the values for the enthalpy, the standard enthalpy of formation, are different. And we use these values to predict the change in enthalpy of a reaction. So a lot of work in chemistry is not done, in advanced sciences, is not done by just experimenting. Scientists do predictions first so that they are not wasting their time on experiments that are not going to yield the desired result. There are many, many tables that are available giving standard heats of formation or standard enthalpies for common substances. I just clipped a little picture of one. You'll have one in your textbook available to use anytime you have a question on these sorts of problems. Here's an example of how you use it. In order to calculate the standard enthalpy for a particular reaction, you need to take the sum. This little symbol here is the capital letter sigma in the Greek alphabet, and it just means take the sum of all the enthalpies of formation for the products and subtract from that the sum of all your standard enthalpy of formation for the reactants. And again, to try to remember which way this order goes, it's alphabetical again because P is before R. So be sure to set it up so it's products minus reactants. So here's an example problem. If we're taking sodium hydroxide and mixing it with hydrochloric acid to make sodium chloride and water, you should recognize this is an acid-base reaction, making an ionic salt and water. Well, we have some standard enthalpies of formation down below. For sodium hydroxide, it's a negative 425.6 kilojoules per mole. For hydrochloric acid, it's a negative 92.3 kilojoules per mole. For sodium chloride, it's a negative 411.2, and for water, it's a negative 285.8. You would note, please, that these are all, there's a 1. The coefficient in front of all of these are, in this balanced equation, is 1. If you are working with a problem and the coefficient is not 1 in front of one of your compounds in the balanced equation, then when you're calculating the standard enthalpy of formation, you have to multiply by the correct number. So if this in front of our sodium hydroxide, if there was really a 2 here in a particular balanced equation, then you would have to be doing 2 times the amount in order to have it as an accurate value for the enthalpy of formation. But since we're not doing that, I will erase that so as not to confuse things. So anyway, back to using our formula. So we need to do the sum of the enthalpy of formation for products and subtract from that the sum of the enthalpy of reactants. And so the numbers are all put out here. And you can see we've got our negative 411 that's coming from our, products coming from our sodium chloride. And then our negative 285 that's coming from water. And our negative 425 coming from sodium hydroxide, and the negative 92 coming from hydrochloric acid. So that when you add all these up and do the math, you end up with the value, a total value of the end, of a negative 179.1 kilojoules, and this should say per mole. The person who made up this slide forgot that part. And so that the heat of the reaction, the standard enthalpy for this reaction, then is listed as a negative 179.1 kilojoules per mole. By that negative number, then you already know this is going to be an exothermic reaction. It'll feel warm. It'll be giving off heat to the environment. Hess's law is also covered in this chapter. And Hess's law, you have a couple of assumptions that chemical reactions may occur as a series of steps, and that the enthalpy of formation of each step can be added together to determine the final enthalpy for the reaction. So this diagram over here on the right shows you how that works. We're starting with these reactants and we want to make this product, but we have several choices. It can follow this way, this pathway to make that product, or you can take this pathway to make that product, or this even longer pathway to make that product. Starting with the same reactants and ending up with the same products, but there's 3 ways to get there. And each one of these arrows represents a step where you have a particular enthalpy of the change in enthalpy of the reaction, or that part of the reaction. Well, what Hess's law says is that the values here of delta H1 will be the same as delta H2 plus delta H3, that they are the same number, or H1 is the same as delta H4 plus delta H5 plus delta H6. So it doesn't matter how you get from A to B. Any of these steps will give you the same answer. The book calls that, uses the words a state function. Other places you might see it's Hess's law of summation. You can sum all of these parts of these reactions together. But it's basically just saying that it doesn't matter how you get to the final product. If you're starting from the same reactants, you can take several different paths to get there, and you will end up with the same change in enthalpy for the entire reaction. So that we can use these formation, enthalpies of formation information to predict what kind of reaction we will have. Here's a little more complicated example of how it works. This would be something that is not part of our course, but it would be part of somebody taking an AP chemistry course or in your college chemistry, so I thought you might be interested in seeing this. Here we have a particular reaction of interest. a chemist wants to make some predictions. What happens if we use sulfur in the crystalline rhombic form and add to it some oxygen and make sulfur trioxide? How much energy would be involved? How much energy would change? What would be the enthalpy change for that reaction? Is it endothermic or is it exothermic? Well, we don't have any information on this particular reaction, but there are some things that are known about other reactions. In this reaction, sulfur plus oxygen gives sulfur dioxide, not sulfur trioxide. And in the second reaction, sulfur dioxide plus oxygen yields sulfur trioxide. So you can see in the looking below, comparing these two, we have the same reactant here as we do in the reaction we're trying to calculate on, and we end up with the same product here, just a little bit different coefficient in front. And so can we combine them? Well, this is where math can be involved in chemistry again. We can use the standard rules of algebra and pretend that this arrow is actually an equal sign and can change the coefficients in front of this equation number 2 by dividing all of them by 2, so that we end up with a formula where you only have 1 sulfur dioxide plus half a mole of oxygen gas, giving you sulfur trioxide. This is the only time that we play around with fractions in chemical formulas. As I said, you don't need to know this. This is just sort of extra stuff. Notice too that we had to change the figure for the kilojoules for this reaction because the one that is given up here is making 2 moles of sulfur trioxide, so the change in enthalpy would be twice as much than if you're only making 1 mole of sulfur trioxide. So let's go to the next slide where I have written it out again and we can kind of talk about what the next step is. So continuing on with this more advanced method in chemistry, I've rewritten those two equations of interest, and we're going to add them together. And what the rules are for adding things together in chemistry this way is if a product or if a substance is on both sides of the arrow, you can cancel it out. And so you then add what's left. So we bring down our sulfur and we add together our oxygens to get 1.5 mole of oxygen and bring down the sulfur trioxide. And we're left with the equation that was the equation of interest. Similarly, you would add together the changes in enthalpy that have been already provided for these reactions. So we would add a negative 296 with a negative 99, giving a predicted change in enthalpy of this new reaction as of a negative 395 kilojoules a mole. So this type of work is done by scientists all the time. It costs a lot of money to try these experiments. Some of the reactants sometimes are very, very expensive, and so it's much better to do the pencil pushing, let your fingers figure it out on the paper, and using the standard enthalpies of formation to predict what will happen in a reaction before you go and actually work with that reaction. So this ends the second video for this module. Now it's time for you to take your textbook and your practice problems and go do some calculations of the enthalpy of reactions using those standard enthalpies of formation.